So in the previous video, we stopped at the stage where we said you have to leverage the cost-based optimizer, and that's the more scalable approach for how you get the best performance out of the system. And the reason for that is SQL is declarative. You typically stop with saying what you need to happen as opposed to how. How do you leverage the cost-based optimizer? So here's where two very specific tools play a critical role. In fact, these are two specific statements that all modern databases support. These are called as explain and analyze, and they are your friends. Meaning you have to leverage them maximally as you go through your OLAP processing needs. And the more you leverage them, the more you actually understand how things work and make informed choices about performance. So let's go one by one. Explain is actually a special statement. So you could attach the word explain to any select query, and it will display the plan that the SQL engine has thought about for that specific select statement. And you could add modifiers to the explain keyword by saying extended and so on, and that will make it look more deep within its optimization modules, and then come back with a physical plan, which is actually going to be much more closely associated with what is actually going to execute for that particular select statement if you have executed the select statement at that particular point in time. So why is this useful? Firstly, it reveals like a wealth of information about the workings of the optimizer. Notice that the optimizer is not just cost-based, right? It's also rules-based. Remember the predicate pushdown we spoke about, where we push down the where clause of column C? That's actually a rule. It doesn't need data for it. It doesn't need to understand cost to do those kinds of predicate pushdowns. That's just a very standard rule-driven optimization that the optimizer uses. Obviously, in some cases, the rules by themselves are not sufficient. Like for instance, deciding which type of join to use, right? Depends on table A being small, table B being small, etc. And what a small means, small is exactly the notion of cost. So that cost-based is also part of the optimizer. So it's a twin optimizer model. And the inner workings of the twin optimizer model are actually quite sophisticated, right? So to be able to get an intuitive sense of performance of your big data job, you probably will need to spend a lot of time with explain on your workloads, right, one by one, and that gives you the cues that you need. The other reason why it's useful is you actually get a very true sense of the performance, and that will give you the clues about bottlenecks that exist. The bottleneck could be the rate given in your select statement. It could be because if you're choosing outer joins as opposed to equi-joins, and equi-joins will get the job done equally effectively, and outer joins are way more expensive. Or you are creating like a distinct set, then also like a multi-set is sufficient. So the distinct operation creates a lot of performance overheads. So those kinds of patterns could emerge, and you would know that by looking at the explain statement. So let's start to take a look at what the syntax looks like. And for this, I'm just going to use the Spark documentation itself directly. So let me switch over here. So with explain, you could additionally add like one of these keywords, like for instance cost and code gen, extended, formatted. Like each of them has their own variants, but the most common thing that you might end up using is extended and cost, because extended takes you all the way through the various levels of planning until the final plan, and cost will give you the bubble up of the cost, right, through the tree, through the relational algebra tree. So let's take an example. I have this specific select statement here. The select statement says select K, sum of V from some kind of a table. The table itself is defined as an alias table T, which has columns K and V, What does a table T comprise of? It comprises of just two records, right? 1, 2, and 1, 3. Then the select statement itself is doing a group by on the key k and then summing it up. So yeah, this is like a hypothetical example. So effectively, what it's going to print as output in this case is 1, 5, right? But yeah, nevertheless, it's useful to understand what happens behind the scenes. So the physical plan that operates here is first it goes through a local table scan. It doesn't know it's actually just constants, right? The logical at the level of the logical plan and at the level of the physical plan without cost involved, it's actually going to just treat whatever syntactically is available with it, right? Without paying attention to the actual costs. So here it's a local table scan. It thinks it's a local table. It's actually just like a bunch of values in memory. That doesn't matter. On top of the local table, it does a hash aggregate. Why is that? Because the group by on key is operating on a column k, and by default, the number of distinct values of k is small enough to fit in memory. And why does it think that? That's just a parameter, a configuration parameter as part of Spark SQL execution, which is basically what is the default size of the keys that you aggregate on, that you assume. So again, these are assumptions, so you can play with it. Yeah, so it assumes the keys are small, rather number of unique keys are small enough to fit in memory. So it chooses a hash aggregate way of doing this hash. What does it push down? It pushes down the sum of v, right? Sum of v, it's called as a partial sum because each of the parts of the table are locally present in the different nodes of the cluster, and those parts are not already partitioned by k, right? Because that's not the table is unpartitioned, right? Therefore, when it computes the local aggregate, it doesn't have the final answer. It only has the partial sum. Yeah. So once it gets the partial sums for the k, then it exchanges, right? And the way it exchanges is by shuffling, and the shuffling is acting on the key such that all the different partial sums for the same key come together. So it effectively uses hash partitioning on the value k. Once it does the hash partitioning, it comes all the different values of k spread across come together. The same instances come together, and then I'm just doing a sum for the partial sum. That's my final answer. That again involves a hash aggregate. Right? So in effect, what you see here is actually the divide and conquer plan for this specific select statement. Right? That's what the explain has revealed to you. Now, if you use explain extended, so here it starts off with the actual logical plan. It started at all. In the actual logical plan, the placeholders not even filled in. So you're going to see at that raw level, then it would have done the parsing and analysis of the select statement, and at that time it will start filling in what is the type of the key. The key here is just a big int. The value is also a big int, so therefore the sum of big ints is big ints. All of that, those kinds of things start to happen, and then it starts to optimize, but still there is no cost consideration here because it's all local, right? Yeah, the cost is not being printed basically. So then there is the formatted version, etc. Nevertheless, yeah. So that's the explain statement. When you want to start working with cost, right? And we'll talk about cost in the cost-based optimizer module coming up next. When you start to talk about cost, then each of the different steps that you see in the relational tree. By the way, this is actually the relational tree also, right? This is the physical relational tree that actually gets executed. Yeah, so when you start to work with cost, then you can turn on the cost mode as part of the configuration. Then at the point, if you come back and execute and explain a statement like this, you start to see cost variables also attached to it. And that makes it really, really powerful to understand where is the cost actually going. Okay, so that's explain. Let's look at its counterpart, which is the analyze. So for the explain to work, for the cost to work, right? the cost is actually measured in terms of two main sets of activities, two main sets of statistics. The first is the number of rows of data that's present in that table, and the second is the size of each row. So then with that we will effectively have the complete size of the table, right, which is the size of each row, the average size of each row times the number of rows. That's your size of the table. So those two cost elements are two of the most basic type of statistics that are required to do cost-based optimization. But you can actually get far more sophisticated statistics also collected, not just number of rows and average size of rows. And that's possible through the analyze statement, right? So just like the select statement can be explained, the analyze table and the analyze statement rather can be applied on a table, on a source table, and this forces the planner optimizer to go collect statistics about the table, both in terms of size of in bytes and row counts. And then for some of these systems like Spark SQL, you can also make it go collect statistics at a column level within a table. Databases like Postgres and Oracle, you could just collect that by default because the settings available for you to do that. In Spark SQL, you'll have to make it do it, which means you could say go at a column level and then collect for that column what are the statistics. Our table level statistics are fairly simple, size in bytes and row counts, but column level, it's where it gets really very sophisticated and also becomes the most useful for complex read operations. So here's an example of how the column level statistics look like, right? So if I did, like for instance, if I had a table in which I had a column name called user ID, so let's say this is the customer master table. Customer master has the set of all customers across all of my entire customer base. So the customer ID or user ID is potentially going to be the primary key, and any join that happens with anything else, like for instance the events table, the payments table, etc., invariably is going to use the user ID as the mechanism to join, right? And any customer service request that I get will be specific to a user ID, will not be across user IDs. So the user ID column becomes like a very important column on which joins happen, group wise happen, aggregates happen, etc. So therefore, it makes a lot of sense for me to analyze and keep it ready. So when I analyze the table, especially the column as well, user ID column, what do I see? I could see a distribution that looks like this. It says the minimum value, maximum value, number of nulls. So because it's primary key, and nulls are 0, which is great. Distinct count is 37,538. That could be the case, which is great. Number of repetitions is not captured here, but then the histogram is null. If the histogram is null, means that it doesn't actually have any value that's occurring in the user ID which has frequency count of more than 1. That's why the histogram is null, which matches with our notion of the fact that the user ID is a primary key. Right? So it's unique. Average column length is 8 bytes, maximum column length is 8 bytes. Great. So this is very, very useful, right? Because now I can start to understand a few things from it. For instance, let's say I'm doing a join of this table on user ID, and there's another table that's also on user ID, but that's the payments table. The payments table is massive, right? What kind of join do I use physically? Notice the number of distinct keys. Number of distinct keys is basically number of distinct values of user ID, and that's 37,000. That's extremely small, easily fixed in memory. In fact, the number of bytes that this kind of a hash table would occupy on the keys would be 37,000, the distinct count times the average column length, right? So that's 37,000 times 8. Which is still, megabytes. Whereas most modern machines have gigabytes. So I can easily construct a hash table which is keyed on user ID, and I could use a hash join family of joins. Whether I use broadcast hash join or not, that depends on the size of payments table. Yeah, so that's why stats play an important role. Okay, let's come back here. Let's look at what the analyze table syntax looks like. By the way, both these are available as part of the Spark SQL programming guide. So come into programming guides on the Spark page, get into SQL data frames. Excuse me. Come here, Spark SQL guide, SQL reference, SQL syntax, auxiliary statements. So that's where it is. Alright, so analyze table, I get the name of the table, and then say compute statistics. Then I could say for all columns optionally, or I could say for a specific set of columns, or I don't specify anything at all, in which case it just computes for the table alone. Right? By default, whenever these statistics are computed, the stats themselves are stored as part of the meta store. So remember we spoke about the meta store where the metadata of that table is actually stored by Spark. It uses the Hive meta store concept. Likewise, the same meta store is actually where the analysis results, the statistics are stored. So it's actually easily available very quick time from the master lookup itself. It doesn't have to query the data again in order to do cost-based optimization if the analysis has happened successfully. Alright, so let's say for instance I have a table teachers just has two rows that I insert Tom and Jerry. Students has two more rows, Mark and John. The students table is actually partitioned by student ID. So now when I analyze the table students and just compute statistics, what I start to get is basically very simple statistics about the table. So I can view the statistics that's been collected by using the describe statement or desk in short. Desk extended students gives me individually what is the statistics that I've collected. So I said I've collected 864 bytes as the size of the data. That's just the size of both of these rows with some overheads attached to it. Then if I compute statistics with scans, so basically no scan says don't go and look at the individual rows, just look at the files that are getting created in the file system and get me the size of the file, right? So it's like an approximation. But the moment I remove the no scan variable, a qualifier, then it actually goes and scans the data. And then that's when it comes back and gives me the actual number of rows that it's found as part of the table. So here it scans the table and comes back with the size. Now if I restrict it to a specific partition, remember we had actually partitioned it by student ID, and student ID is actually just two number in this case. So I could restrict my analysis to only the particular partition, in which case when I describe it, I get the answer for, I get the description, like the stats for that particular partition. Now if I take column name, the name column is actually Mark and John, strings basically, and if I analyze based on that, I start to get the distributions for that column. So that makes it specific and interesting. Alright, so that's the analyze step. So with this, we will just pause. We'll pick up in the next video. How do you put all of these concepts together and start to work through your optimization pipelines?